Yeah, hi everyone. Let's get started. Okay, so before we start, a couple of announcements. Homework 1 was due yesterday. I think everyone submitted it. How did it feel? Yes, no? Great, thank you. Homework 2 is out. It will be due February 6th, and the cluster is down until through this Thursday. But you can still download the homework and take a look at the PDF. And I suggest that you do. Suggest that you try to start this earlier rather than later because it is a bit more complicated than homework 1. So if you have any questions or run into any issues, please just post in the discussion board. So today we're gonna do more data structures. Last class, we talked about binary trees and skip lists, which are classical data structures in the red model. Binary trees like self-balancing ABO, and skip lists are these probabilistic data structures. And these are not IO optimal. So we talked about the IO cache model with cache line transfers and measuring things in terms of B and I guess in data structures, it's mostly B, like you don't really see factors of M. So measuring things in terms of B, and we talked about B trees, B plus trees, which are these self-balancing trees, and B epsilon trees, which are these buffered B trees. And both of these are IO optimal because there's a lower bound curve based on this trade-off between insert and query, but both of these require knowledge of the cache parameter B. So you have to set the node size to something like theta B. Oh, sorry, could you please turn away your laptop? Thank you. Great. Yeah, I just wanted to clarify something from last class before we move on. So there are some questions after class about how you prove the bounds for B epsilon trees. So this is the same picture as last class. This is the B epsilon tree. You have B epsilon pivots, and then you have B minus B epsilon buffer space in every internal node. And these nodes are just, they're not buffered, there's just like elements in the bottom. And so basically the way that we're going to print this in each internal node is size theta B and theta B slots. So to read each one, it's going to take theta 1 IOs or cache line transfers. You have B epsilon pivots and B minus B epsilon buffered elements. And like I said, each time you flush things down, you pick the child that's going to get the most stuff going to it, and you flush stuff to it. So that is going to get at least, this is the buffer space of B minus B epsilon, the whole thing divided by B epsilon, because you have B epsilon pivots. This is omega B1 minus B to the 1 minus epsilon. It's like, this is B to the 1, this is B to the epsilon, you divide, that's 1 minus epsilon. And so that's how many things, at least how many things are going to go down every level, every time you flush. So we did theta 1 cache misses, and we're going to move this amount of stuff down. So the amortized cost per element is 1 over B to the 1 minus epsilon. Does that make sense? And the height of the tree is over there, but it's log base B to the epsilon. And so the amortized cost to go all the way down is the height of the tree divided by the cost that it takes you to move down 1 level. And that is how you get, this is on the lower bound. Yep. Great, thank you. So we're going to do IO efficient data structures again, and more of them. So this is the picture from last class. Oh. Yes, I am recording. Okay, great. So this is the picture from last class. And again, there's like these two extremes in the trade-off curve. There's logging, which is like you just append to the end. And then there's indexing, like B trees. And indexing is like everything is perfectly arranged in sorted order. And logging is you just write to the end, which is really fast to insert, but searching is really hard because now you have to look through the entire thing. And neither one is like best in some sense because like inserts are faster in logging and searching is faster in B trees. So again, this is this lower bound curve, and on one side you have fast queries and slow inserts, and that's the B tree, and on the other side you have logging, which is fast inserts and slow queries. And this is the optimal bound we proved, and this is what we proved that both B trees and the epsilon trees can achieve this lower bound as a function of epsilon. And so B trees are optimal for search, but not for updates. Like we showed that you can get asymptotically better updates using buffering with the same asymptotic point query cost. And the goal is to get a data structure with inserts that are better than B tree inserts without sacrificing asymptotically in queries and ideally practically as little as possible in queries. And this is the promise of right optimization, which is a larger class of data structures, and B to the epsilon trees are one type of right optimized data structure. Okay, so today we're going to talk about another kind of right optimized data structure, which is called log structured merge trees, also called LSM trees. And LSM trees are not optimal, so they're not on that lower bound curve straight out of the box, but we're going to show how you get them to the optimal curve. So LSM trees are a type of right optimized data structure. They were proposed by O'Neill, Cheng, and Golick in 1996, and they use right optimized techniques to significantly speed up inserts. And recently, I guess not super recently, in the past 10 or 15 years, they've become really popular. Like LSM trees are under a lot of these really popular key value stores. There's a couple of examples like Accumulo, Bigtable, BLSM, Cassandra, LevelDB are all built on LSM trees or some variant of LSM trees. So these are super popular in actual implementations, and we'll go through like exactly what they are and kind of why they are so popular. Okay, so at a very high level, an LSM tree is just a cascade of B trees, so like a whole bunch of B trees. And here are some trees. They're indexed like T0, T1, T2, and T3. So in this LSM tree, we only have 4. And each tree, T sub j, has some target size T sub j. And the target sizes increase exponentially. And typically you go up by factors of 10 in size. So like size of Tj plus 1 is about 10 of Tj plus 1, but this could be any constant. And in the theory, this can be even super constant, but in terms of practical implementations, this is usually constant. Okay. So the way you do point queries is like, since each of these is a B tree, you just do point queries the way that you would normally do point queries in a B tree by traversing the tree structure. So like you would first look in T0, and if it's not there, you would look in T1, T2, T3, and so on. And yeah, so that is pretty natural. And when you do range queries, like range queries are this operation where you want to get all elements, for example, between X and Y, like all elements that are between 100 and 200, then you do a point query to the start of that position. Like in my example, you would do a point query to the start of 100, and then you would scan forward in your B tree until you got to 200, and you return all elements that you found in that range. So this is pretty much like, this is just B trees, but now you have a whole bunch of them. So you just do the same operation in all of them. Okay. And insertions, you always insert elements into T sub 0 first. And this dark part means like how full it is. And so you insert into T sub 0, and then when it gets full, you flush your elements into T sub 1. And when T sub 1 gets full, you flush into T sub 2. And this example, T sub 2 got full. So now we're going to flush it into T3. So now T2 is empty, and T3 has more stuff in it. And you rebuild T3 and T2 after a flush. And like the same for any pair. Like if you flush T1 into T, yeah, sorry, go ahead.
So are they sorted then by value, by the key somehow, or?
They're B trees, so B trees are sorted by key.
No, I mean, but with like between the trees themselves.
No.
So, okay.
Not necessarily.
How can we end up with not doing fully one tree and insert inside the other, like previous life? So to insert in other trees, we should have inserted first in the first one, and then got it full, and then the flat. And then basically, that's the only way we can insert in the following tree, right?
Mm-hmm. Yes, exactly. You don't ever insert directly into the later ones. You always insert into the smallest one, and then when the smallest one gets full, you keep flushing downwards.
We're just showing it growing from the bottom, but it actually grows like from the top, right? Like these are just regular B trees.
These are just regular B trees.
But I just want to make sure it's growing as a regular B tree, even though
yes.
And then the other question is, what do you mean by super constant?
Super constant just means like little omega of 1, like just like log n, for example, or B is not a constant in the cache line model. Yeah. Thanks. Yeah. I guess it depends on like how you think about B trees growing, because like when I think about them, like you start with a root and then one gets promoted. So like when I think about it, they grow up. But does that make sense? Either way is fine. Like do trees grow up or down? I don't know. Yeah, it doesn't matter. Either way is fine. But yeah, so this is just like how full it is. Yeah. And in this illustration, they're growing from the bottom. Good. So yeah, so when you get one of your trees full, then you just flush it into the subsequent one, and then you rebuild both of the neighboring ones. Okay, and yeah, this is kind of like going along with one of the questions from last week. How do you do deletes in a buffered tree? So this is again like a buffer data structure, and deletes are kind of like inserts. So when you want to delete something, you put a tombstone message in, which has some special value that tells you that it needs delete, and you put it into the smallest tree. And when it meets an insert of the same element, then they cancel each other out and the delete stays, so that you flush it all the way down into the bigger trees. This is also how you do deletes in buffered trees, how you cancel them all the way out to the bottom, because you don't know like what's below you. And when the tombstone gets into the same tree as the element that it matches with, then it just cancels out that element.
So does that like on the way, exactly like the key value that it's about to delete, right? So basically we just take one place in the tree and then,
Yes, yeah. Like it would have the same key, but as a value, it might have like max int or something, and then you just reserve max or 0. Yeah, good. So yeah, but they like as data, they act exactly like inserts. They also get flushed down to later trees.
what about duplicates?
What about duplicates?
Yeah.
If duplicates can appear in different trees, but the most recent duplicates are always in the smaller trees. It's like
So the tombstones don't get passed through all the way to the end.
the tombstones, they do get passed through all the way to the end. Like you can only have one copy of each element in each tree. Because when they get flushed, like you would rebuild the whole thing and you would just take the most recent one.
But how do you know? Like, for example, I flushed already my value from the very first tree to the very last. Then I have my tombstone somewhere in the middle.
Mhm.
And then I have my very first tree not full. And then I insert again this exactly element. So I wouldn't check all the other trees there, whether they contain it or not, right? I'll just insert it and
You
then
have,
I would have element tombstone.
yeah, you'd have to search from the beginning. Like when you do point queries, you search in the smallest one first.
Okay, yeah.
And so you'd find the insert earlier than the delete.
And when I insert it, then I'll overwrite the tombstone or we just delete it or?
Yeah, you would just overwrite it. You would take the earlier one, or sorry, the most recent one takes precedence.
Like, is there like some optimization where like we can delete tombstones on the last tree or something, just to make sure we don't like fill it up with just.
Yeah, like when you do the rebuild at the
Yeah.
very last one, then if you don't find anything that matches the tombstone, then you can just delete it.
So if you're searching from T0 and you get a tombstone, you keep searching? Or do you?
No.
Because what if there was 2, and the tombstone was supposed to knock out one of them? But.
Like if there was one here and then you search and there's a
There was
tombstone.
there was one in T4 and one in T3, and then there's a tombstone for it in T1 that was supposed to knock out T2. How do you know that the one in T3 is still on?
The tombstone in T1 should eventually cancel out both in T2 and
Oh,
T3.
T3 means both the elements?
Yeah, it like a tombstone should cancel like all the copies that came earlier.
There's no both, you're right. But-
You're right. But like it is confusing, like there can be multiple copies, but only one is like the valid copy. And that's the most recent one.
Tombstone would occupy some memory than any. Pass it to the last tree, you free up the memory as well in the last one.
Yes, yeah, when you pass it here, either it cancels something out or it doesn't, and either way you delete the tombstone.
No, so, say you enter the tombstone that you know the first tree. There if you find an element, you knock out it, but you still have to keep the tombstone to be traversed to the last tree.
Yes,
In the last tree, after knocking out or not, you just free up the spaces.
yes, yep, exactly. Yep. Thank you. Yes. And yeah, so that's how deletes work. And this is good because now it clears out how you do deletes in the buffer trees also. But instead, in the buffer trees, rather than bigger trees, you just like, it's just lower levels of the tree. Okay, great. So this LSM tree is this example of there's a technique called static to dynamic transformation from Bentley and Sachs. And basically the way it works is that you can build this dynamic data structure out of static data structures. And so like, you can notice that each of these B trees is a static B tree. And so the first one is of size B. So like in a theoretical sense, it doesn't really matter what you do in it. So it can be a static B tree. And you can rebuild it every time because in our model, just moving one cache line is order one, and whatever you do in that cache line, it doesn't matter what you do in the current computation. And then each one of these later B trees is static, and then you completely rebuild it upon a flush.
When you say completely rebuild, do you mean you take all of them and insert them in some order? You take everything like already, so say T2 to T3. You take everything in T3 and everything in T2 and put them in some order and then reinsert them, or?
You
what do
can-
what does rebuild from scratch mean?
Like you can merge two trees, like imagine two binary trees, both of them are in sorted order.
Yeah.
And so like you can imagine one way to merge two trees is like you flatten them both into an array, and then you do like a 2-finger walk, and then you get a new array that has both elements from T2 and T3, and then you can rebuild the tree from that array.
Yeah, so as long as it's sorted order. Just-
Yeah,
okay,
Exactly.
gotcha.
And like all the trees are already sorted because they're B trees.
Yeah.
Yep. Good. Cool. So yeah, that's how that works. And remember in our model, we parameterize things by B. So in a B tree, searching takes log base B of n, which is log n, log base 2 of n divided by log base 2 of B. And then searching an array takes approximately log base 2 of n modulo the last search in the single block. So searching in a B tree is asymptotically faster than searching in an array in this model. Okay, so we're gonna analyze how you do the point queries. And so remember that basically the way it works is that you have these asymptotically increasing sizes of tree. And here, if the trees are increasing by a constant, the number of trees that you have is log n. Because you have n elements and each one is decreasing by approximately like half or more, but it's a constant, so it's log n. And I'm ignoring the base here. So it takes, this is a B tree, it takes log base B of n to search in the latest B tree. This is like a worst case search, like if you only could find it in the last one. It takes log base B of n to search in the last B tree. It takes log base B of n over 2 to search in the second to last B tree, assuming that these are like going down by half, because it's easier to do the analysis that way. Then the one before that is 1/4 the size, and so on, until we get to the smallest one, which is size B, and that's log base B, which is just 1. Log base B of B is 1. Okay, so log base B of something is like log that divided by log B. So you can pull out log B, and now you get this series, log n plus log n minus 1 plus log n minus 2, because that's how like divides in logs become subtracts, and this is log squared. So log squared divided by log B is log n, log base B of n. So this is worse than searching in an array because that was log n, and also worse than searching in a B tree because that was log base B of n. So it is not on the lower bound. Okay. And this is how you do the inserts. So the cost, like I said, like you can rebuild the tree by flattening it and doing a merge. And so the cost to flush the tree of size X is X over B, because it takes X over B to read the tree because it's a B tree. It takes X over B to flush it. Yeah, it takes X over B to flush it because the next thing is also within a constant size of it. It takes big O of X over B to flush it, and flushing and rebuilding it, the easiest way to do it is to flatten it and then merge the arrays and rebuild the tree. And the number of times that you have to do this flush is bounded above by log n because you have log n trees. And so the insert cost is log n divided by B amortized transfers, because it costs you 1 over B per element on each flush to flush it, and then you had to do a log n flushes.
Can you go back to the previous slide?
Yeah, for sure.
So, I get the first step. So how are you like log n plus log n minus, like, I guess it's like log n factorial, and that's like approximately log n all squared.
Yeah, like summing up numbers
Oh, because
I up to is n squared. It's order n squared.
you're not summing up the numbers, right? You're multiplying the numbers.
You're summing the logs, like log n plus log n minus 1 plus log n minus 2. And then but like I just wrote it in reverse, like you're starting that way. Now you're good. That make sense? Cool. So The insert cost is amortized log n over b. Okay, and this is again like this optimal lower bound. This is the insert cost, this is the point query cost, and the LSM tree has this factor of log base b in the search, which is suboptimal, and we would like to get rid of it. Okay, so the problem was that we had to look at all of those trees, which is what got us the log squared. And there's several ways that we can improve it. One, we can use caching. We can use bloom filters, which we talked about a little bit last time, but actually I want to talk about it more in depth today because it is actually interesting. And this technique called fractional cascading that I'll go through later. Okay, so caching is like not like it doesn't show up in the theory, but from a practical point of view, when you search in the small trees, those trees are probably in cache because they're warm and like you flush into those most frequently. So those are probably higher up and you don't have to pay so much to access them. And so ideally you find them in there and then things are free in an asymptotic sense. Okay, so that is something natural that you don't have to manage. Filters. Okay, so like I said last time, a dictionary is the set data structure. It maintains a set S from a universe U. And this is an exact dictionary. So like this is your universe. You have A, B, C, D as your elements. And like S is your set, which is this blue circle. And A and C are in your set, and B and D are not in your set. So A and C are members in your set, and B and this should say D are not. And a dictionary, like you can naturally do membership queries on S, like any of these data structures that we're talking about, like B-tree and so on, are dictionary data structures. A filter is this other class of data structure. It maintains an approximate dictionary. So suppose that the filter is on the same set of elements here. And a filter would say that A and C are members of your set, but a filter can have one-sided error. So it may give you false positives. This should say D, sorry. But it might tell you that D is actually a member of your data structure when it is actually not. So you may have errors rather than an exact dictionary where you know for sure that your thing is in it or is not. And so you get approximate membership queries with some probabilistic guarantee. And filters have one-sided errors, so you can get false positives, but you can't get false negatives. Okay. And the way that filters give you this guarantee, if your element is in the set, return yes with probability 1. So if you see yes, then you're always guaranteed that your element is inside the set. But if it is not in the set, you see no with some probability 1 minus epsilon, which is your error bound, or you see yes with probability up to epsilon, which is a false positive. So if you see no and it was actually no, that's called true negative. And if you see yes, but it was actually no, then it's called false positive. And like I said, this should say false negatives. There are only false positives. There are no false negatives. And if you enable these if you allow a little bit of error, you get to be way more compact than a regular dictionary. So a regular dictionary, the space is bound, if you have n elements, the space is bounded below by n times log of the universe, because this is how many bits you need to represent any element, and you get n elements. So it's pretty big, but in filters, you get n times log of 1 minus epsilon, or 1 over epsilon, where epsilon is some constant error bound. Yeah. So the thing on the left, n times log of 1 over epsilon is much smaller than the lower bound for your dictionary size. And the classic filter, like the most original filter, is called this Bloom filter. And the way it works is that you have a bit array and you have k hash functions, and the hash functions and bit array are set independent of your elements. And in this example, we're going to say that we have 2 hash functions. Okay, and we're going to start with this set. So in the beginning, like in the beginning of the time, your set is empty, and we have some elements in the universe, A, B, C, and D. And okay, so let's say we get A in our set. So we're going to use our 2 hash functions, h sub 1 and h sub 2. And suppose that h sub 1 gave us 1 and h sub 2 gave us 3. And the way that the Bloom filter works is that to insert something into it, you have to set the bits that you got from the hash table, hash functions. So this is 1 and that's 3. So now slots 1 and 3 are set and everything else is empty. Okay. So now let's say we got C into our set. And so C gave us, like the hash functions gave us 5 and 3. And so this is 3 and this is 5. Okay, and notice that there's some overlap. They don't have to all be different. Okay, so we're gonna ask, is B a member in our set? Well, we use the hash function in the same way. We look at h sub 1 and h sub 2, and that gives us 2 and 5. This is 2 and this is slot 5. And if both of them are set, then we can return yes. And if at least one is unset, then you return no. Because like if it was in there, both of them would have to be set. And so you see that this is 0, so you can say, no, it's not in the set because at least one of the bits was 0 in the Bloom filter. Okay, but whatever we wanted to ask if D was in the set, then like suppose our hash function gave us 3 and 1, and these are the same bits that we had just set. So the filter would return yes, even though D is actually not inserted, it just happened to overlap with the things that we already had inserted. And so that's where you get the false positives. Okay, so one issue with Bloom filters is that out of the box, they don't support deletes because suppose that you wanted to delete C, which bits would you unset? So like the two hash functions that you got are 3 and 5, but some of them overlap with the other elements. So if you delete one of them, then you're like unsetting bits from other elements as well. So I'm not going to prove this, but you can show that a Bloom filter that has some positive epsilon, false positive rate epsilon uses 1.44 times log 1 over epsilon bits per element. And for epsilon, for an example, like if epsilon was 2%, then the bits per element would be about 8. So that's like 1 byte. And so usually like for this pretty low false positive rate, you use 1 byte per element, which is much smaller than normally in your dictionary. You have to use at least 4 or 8 bytes per element, like if you're using int32 or int64 or something like that.
So the size per element only depends on the error rate, but not like the size of the universe. I'm assuming the error rate is like calculated based on the size of the universe and it's based on how many represent. But try to understand how you could use 8 bits per element for both a very small universe and a very large universe. Does this approximation break down?
There's something that is hidden here, which is like you kind of how many slots should you allocate in your Bloom filter, and that is also dependent on the size of your data set.
Yeah.
And so like if you don't know the size of your data set up front, you might have to rebuild your Bloom filter every once in a while.
Okay.
And so like given number of bits proportional to the, like if you have number of bits data of n, which or n is your number of elements, then you can set the false positive rate.
Oh, okay, so
Yeah.
that's why you can have a fixed number of bits per element.
Yeah.
instead of have many more slots.
Exactly, because it depends, like the number of slots varies depending on your input size.
Okay.
How will the hash functions chosen?
How are the hash functions chosen? You can choose any independent random hash functions.
Are all vectors binary arrays, or can you use like counts instead of binaries for better than how do you use it?
Yes, so yeah, good point. So one variation of the Bloom filter is that instead of doing bits, you can do, I don't know, like shorts or ints, and then you could count, and then that would allow deletion, but then you have to pay more space. So, yeah, exactly. And then another issue with Bloom filters is that you can check for membership, but you can't actually get the elements back. Does that make sense? Like, you have to, if you only get the Bloom filter, how would you know what the original elements are? Because the bits that you set are just a result of the hash function.
You mean like the key value?
Yeah, like you hash the key to determine what bits to set in the Bloom filter. But if you want the actual key back, you have to maintain some auxiliary thing.
But if you have it, does it ask for it? No response.
You have it in the request. Oh, but if you want the value, I guess.
Uh,
Well, I
sorry.
mean, also, you don't know, like,
like, if someone else set the key,
Mhm.
like, you wouldn't know, but in a dictionary, like, to the structure has the source of the key, in a Bloom filter, you aren't storing. the
Yeah.
key.
I guess, yeah, maybe another problem is like you can't like do iteration over the elements. Like you can't be like, give me everything in the set. You can only be like, is X in the set? Mhm. Yeah, so that's Bloom filters. And Bloom filters are this classical data structure that you see everywhere. They're in computational biology, databases, networking, storage systems, and streaming applications. And today, the one that we care about most is storage systems because we're talking about data structures, but they are in a lot of other places. And there's been a lot of really interesting work, like because they have these limitations, like I talked about, like you can't delete and you can't get values back and you can't iterate over the elements and stuff like that. There's like a lot of variations on Bloom filters trying to address these shortcomings. Yeah, so Bloom filters are the most common type of filter, but there are a lot of other types. There's quotient filter and cuckoo filter, which can support deletes. And these three, Bloom, quotient, and cuckoo, are dynamic, which means that the set of element is not known in advance. And there are other ones like XOR and ribbon that are static, where you know the items in advance, but you can get better space bounds if you know them in advance, because you can like set the data size up front. That make sense?
But for available Bloom filters, we do like pre-allocate a size, like we don't know which
Yeah.
items are gonna be in there, we have an estimate of how many we want to support, right?
Yes, you have to pre-allocate some size, but like, once you get big enough, you may have to reallocate.
Allocate and change your hash, change how your hash functions work, or,
Yeah, you have to rehash everything into it.
oh, so
Like you have to completely rebuild your. Bloom
which means you
filter.
have to throw away everything you have.
Yeah.
Yeah, 'cause you can't.
Yeah, you might just like double or something.
Mhm.
If you didn't know upfront, but it like, in a theoretical sense, it like amortizes against your inserts because you inserted n elements.
Like you lose the ones you inserted, you don't lose the ones you inserted somehow?
Well, no, you still have them, because you know which like places were set, like if bit 3 was set in the original one, you know, like if you doubled it, you know, like where that set bit would go, so you wouldn't lose anything.
That's not like, how do the hashes work through? How do the hashes now start using all?
Yeah,
those?
no, you do need to keep a full dictionary underneath because.
Okay, so yeah,
Yeah.
you can do, okay.
The
You
Bloom
have to get a
filters.
list of everything.
Yeah, the filter, you need, yeah, to rebuild it, you do need a list of everything that you had in the past.
Okay.
The filter is like usually the filter is usually not a standalone thing, it's usually like on top of something.
Wait,
that
I'm
makes sense.
confused, because like you have, like the original, let's say it's an array of size n bits, right? And so those bits are like set,
Mhm.
you have the set bits. So like, if you wanted to double the size of the array, like, whatever the, or I guess, like, you change, I guess, why would?
It's just, it's subtle, so like, the hash function depends on both your element and the size of your thing, because usually it's like mod. Your hash is like usually like mod whatever the size you had.
Yeah.
But you don't know how to get it back.
First slide for the filter, there was like the size of the dictionary is n log size of the universe.
For the dictionary, yes.
How do you, what is n here?
Oh,
Well, just good.
n is like the number of element, I don't want to go all the way
You
back.
need like logs of bits to
Yeah,
distinguish everything in that elements, so that's.
Yeah, so like, the universe size is u, so you need log of u to hold each thing, and then you have n elements.
That element's already placed.
Yeah, so like if you're trying to analyze the size, let's say you wanted to hold n elements, like how big your data structure have to be. It takes log u to hold each element, and then you have n of them.
Oh,
Yeah, this is just like, if you already had n elements, how much would you need? And like, this is the lower bound, but like, when you have trees, like you might have pointers and stuff, so you might even have more space than that.
okay, you can go ahead first.
Sorry.
I was thinking in the thought that, so say you have an array for dictionary and say a bit array where the number of bits is log u, then you can basically,
The number of bits is log u. When did the number of bits need to be u? Like you're saying like you would just set the bit if the thing
Yeah.
was in there? Then you need u bits.
Yeah.
You're good. Sorry, you had a question.
so suppose we have blue filter and the filter is full at a time.
And at that time, we have to like double the size of the filter, and the hash function has also been changed.
Mhm.
Because the size, because the size changed, and this time also we will calculate all of the.
You need to keep like a dictionary underneath or something to be able to do iteration.
But in this scenario, the space complexity is also like equal the space of the normal dictionary. There's no advantage of using.
Yes, like in terms of actually just storing this elements, there's no advantage of using the dictionary. But in terms of like, if you only had to query the filter, I'll talk about it later, but the main reason that you have the filter is that like you save accesses into your dictionary. And so if you can save access, then you can query this much smaller thing.
So if we can guarantee that the sizing has been enough, we don't have to store such normal dictionary, so that space complexity is increased.
Yes, you still probably have to store the dictionary, but the dictionary may be stored like somewhere else, like on disk, for example. Whereas like the filter can be stored in memory.
Yeah.
Like if
Yes, if the false positive rate was much, not like a constant, if it was something polynomially small in n, then it would be much bigger than the dictionary.
So in that case, it would be better.
Yes, yes. You have to allow some constant like error.
This one, do my
Oh, sorry. I'm sorry, dude.
With the dictionary, like we know the size of the universe, but I think you could design a filter that is more perfect. We can have a fun with the universe that's run by bigger. Like you might design your filter to be more exact than the universe, you know? Like if your error rate is, like if the universe is only 10, your error rate is 1%. And nothing errors, and it's like you could have a worse filter that's more precise than possible, right? I think that's why it could be worse.
Yeah.
I mean, like in a dictionary, I'm assuming like there's also some hash function where like to figure out where we're storing it. So I guess, or like, where does the benefit come in like,
I think the benefit is like, because the bloom filter is smaller, so you can like store it, and it's like, what you were saying, the dictionary could be on disk, so you don't wanna query the dictionary all the time, so you query the bloom filter first, and then if you have to, you query it.
so it's more of like a cache.
Yeah, it's more of like it's usually not like a standalone thing. It's like with a full-on dictionary,
Yeah,
but it allows you to like use the overall thing more efficiently.
Yeah, but that's due to like, because you're storing like a dictionary on disk, and like this is a cache, it's
Yeah.
not like asymptotically just better.
I mean, like, if you do see yes, you can check fewer bits.
Okay.
So like it's constant time to check
Yeah.
the hash functions. So like if you see yes, then you don't need to check the dictionary. If you just want membership, like if you just want yes or no, you don't need to check the dictionary once you see yes in the filter.
I mean, well, like, because of the false positives, you do, right?
Sorry, no. If you see no, you don't need to check
Oh,
the, sorry, I mixed them up, yes. If you see no, you don't need to check the dictionaries, you can save your search. Yeah, so going back up one level, so we just talked about Bloom filters, and this is how you use Bloom filters in this LSM tree. So you can avoid queries for elements that are not in a given B tree in an LSM tree, so you just put a filter on top of each one of these. And if you see no, then you don't have to keep going, and only if you see yes, you have to keep searching for it. So suppose that we have this workload with A positive and B negative queries. I think these are flipped actually. No, this is right. Yeah, so if you have a dictionary level filter, you would have to access it A plus B. And if you have a level filter, then you have to access it A plus epsilon B. Because epsilon B is the false positive rate. Okay, so I'm gonna move on from filters, but that's really good. So now I want to talk about this technique called fractional cascading, which is specific to LSM trees. So the filters thing is a more general thing, like you can use it on top of any dictionary, or it doesn't even have to be a dictionary, just like any application that might need this approximate membership. But fractional cascading is a specific thing for LSM trees, which is Uh, basically, the high level idea is that we're already searching in the lower trees. And in a naive LSM tree, you just kind of like throw away that information that you got and you have to do the search from the top in the later LSM trees. But like, what if we use that information somehow to search in the later ones? Especially because we have to rebuild them anyway, so we might build a smarter structure to use some information between them. Okay, so this is an example. Suppose that we wanted to look up this element C, and we have two trees, T sub 1 and T sub I plus 1, and here I'm just illustrating the leaf level of both LSM trees, or both B trees in the LSM. And if you look up C, here, you know that it's between B and E. And you know that it's not in this top one. And normally, like, this is what your LSM tree would look like, and you would have no knowledge about what's down there. But instead, what if, like, we have to rebuild them anyway, so we can rebuild the structure to give us pointers between these elements, or between these trees. So we're going to add forward pointers between the first tree and the second tree. And so once we search in the first tree, we can use the forward pointer to jump into the later tree. So here, we would put this forward pointer between B and E, and that would be, or from B. I guess each pointer is from one element in the earlier tree, and you would point to where it would be in the later tree. So B's pointer goes here between A and C, and we would search and we would find B here, and then we follow this pointer here to C. So instead, ideally we would get closer to where we would have to be.
What, when would you add that point?
When you rebuild T sub I and T sub I plus 1. Like when you flush from T sub I into T sub I plus 1, you completely rebuild both.
Oh, okay, so when you're, no, yeah, that makes sense. When you're flashing T sub I, it's not like, you're not removing all of those elements.
No, you're not just like calling delete in T sub I repeatedly and adding into T sub I plus 1. Like it is more efficient to just like flatten them and rebuild them.
They only go between leaves.
Do they only go between leaves? If it was a B plus tree, it could only go between leaves. If it was a B tree, you probably need to do the internal levels too. But-
Wait, if you're just, you're not deleting, but you're sliding and rebuilding them, how do you know that you can like overwrite like what's in there?
How do you know that you can overwrite what's in it?
feel like
You merge them. You don't delete anything unless you have a tombstone.
Well, so you have like T sub I and then T sub I gets full, and so you flush all of those to T sub I plus 1, but you know, T sub I still has those elements, right?
No, they're gone from T sub I. T sub I is now empty.
Okay, it's not, well, so then, how are these pointers are still there? Or like, no, they're still there, but like, these pointers are there now?
No, I think this is the image after you rebuild. So
Yeah.
your example doesn't apply to the image because image implies that T sub I is full. And in your case, it wouldn't have any pointers because we wouldn't have any elements there,
Mhm.
right?
Yeah, so in the case where, yeah, I guess like this doesn't work in the case where it's completely empty, but there are sometimes cases where like there's stuff in both of them. Like earlier, we had the
Yeah,
case where like
there's
the
stuff.
trees are varying levels of full.
I guess I'm confused, like when there's stuff in both of them, I don't know, like when.
Yeah, I agree. I mean, when exactly do we do this, insert this forward pointers? Because like, if we flush and then we rebuild the second tree, so the first tree is empty anyway, so it wouldn't have any pointers, right? Because we just flush the whole elements, flatten the next tree, and then rebuild it from the beginning.
Mhm.
So when exactly does this forwarding pointers happen in this process?
I see. It would have to be when there's stuff in the previous tree.
Again, when does it happen? I mean, like, I have, at every step, I have some stuff, right?
Mhm.
So do I consider all these forwarding pointers at every step and like recompute them and like forward them, or does it happen at like when something happens?
I think you build the forward pointers only when you insert elements into any of the
Okay,
subsequent
so
trees.
by insertion, I also track this forward pointer.
Not on every insertion, because the insertions just go into the smallest tree.
Yeah.
But on later insertions. No, I see your point,
Yeah.
though. Maybe you do have to keep them.
You keep them how do we add following
Maybe you flush the leaves only and then you keep a B tree and then you keep the internal levels? No, because this is leaves.
Mm.
You keep this.
So yeah, if you, so when you just push the leaves, you know where they went and you can just backtrack to the upper level and just point at that. That might work. If you're just touching the leaves.
Yeah.
You know the values in the upper level, the level just above.
Mhm.
And you know how the point is. So that level.
Yeah, like you know the levels with, you know that within one tree, like what the upper level goes to the lower levels in the tree. But this is for like between trees.
Yeah, so, say the T naught tree gets filled.
Mhm.
And you want to just flush the leaf to the next.
No, we don't flush on the leaves, we just want to hold the leaves, and we also the key. But as I imagine this myself, when every time we insert an element, we search anyway all the trees, right? Okay, till the point if we found one, then we don't do this, but if we didn't find one, then we do this. So, and then we checked the whole thing, and basically by every insertion, we would also insert this forward pointer, because we anyway checked the whole piece, right?
Mhm.
So that would be my guess, but I'm not sure. I don't know.
So say the ACDF part was in 3 TI
Mhm.
for this step. And then it got filled, so this specific leaf was pushed to TI plus 1.
Mhm.
Then you know where the predecessor was B and E.
Oh, you're
and
right.
then you can
Yes.
point them out.
Okay, good. Yeah, that's it. Does that make sense?
Yes.
Yeah. Okay, so yes, so these elements had to be before in T sub I. And so you know which, no, maybe that doesn't work because they might be in different leaves depending on the structure of T sub I now. But you know,
Yeah.
I mean, this also means you're not doing a full flush. right?
Yeah, only in case of when you were flushing the leaves. not
Yeah,
the
only
leaves.
flushing.
no, you should flush them all, I think, in regular LSM.
But it doesn't make sense to flush only the leaves because I think it wouldn't make any sense to flush only the leaves, right?
No, you should flush the entire thing.
10 pointer.
You maintain this when you have intermediate stuff in between. You maintain this when you have intermediate stuff like in both levels, in both I and I plus 1. And maybe you only flush half the stuff. Like in an asymptotic sense, it is fine if you only flush half the stuff.
And if you flush half the stuff, then you know
Yeah.
where you can place the pointer.
Yeah, from like a big O sense, if you flush half versus the whole thing, it doesn't matter. So maybe that's how you do it.
Only if you not flush the entire thing.
Yeah, maybe I think you're right. Like maybe you just have to flush half the stuff for like a little bit less than half this, or like a little bit. If you flush anything less than every single thing, then you can build this. Okay, that's probably right. Sorry. Yeah, you can go first.
What will happen in the case of B trees? Because like if it's B plus trees, you only have point of the leaf. Then B trees, even the intermediate layers can have points of view.
We can assume that it's B plus trees. I guess that everything B plus trees are like pretty much everyone would use them rather than B trees because they have everything in the leaves anyway. Make sense?
What point is designed to like help?
Yes, they're designed to help search because like if you search in this earlier tree, then you use them to point to a closer location in the later
If
one.
I'm looking for C and it's not in the T sub what I, then maybe, I don't know, so like instead of searching T sub one I and then searching T sub one I plus 1, I can add forward pointer and I'm searching that. Oh, then he is pointing to the one before C. And then the next time I search C, I can get it faster because I can just do the forward point instead of like searching someone.
Anytime you search C, you should be able to find it faster because if you have to search this one earlier, then you can follow it closer to C here.
So the problem is like one hour adding the forward point.
Yes, I think we just figured out like you add them when you flush, but you don't flush every single element. Because when you flush every single element, then you don't have anything to point from. So like if you flush a constant fraction of the elements, all your bounds still hold, but you can build these forward pointers now.
I'm confused with the B plus tree question. This wouldn't work in B plus tree. point.
Why wouldn't this work in B plus trees?
B plus tree only has values of the leaf.
Well, B plus trees has internal levels, but the elements are replicated in the internal levels. Like B plus tree, everything appears in the leaves and some stuff is copied into the upper levels to help you search.
Oh, I mean, not necessarily stop, but like separators, so to say, because like you might not have an element in the leaf, but you might have it in the inner node in the B plus tree.
In the B tree, in the B plus tree, everything
yeah.
is in the bottom.
I think his point is that we can build these forwarding pointers during query.
Yes, you can also, you can build it during query, but I think you want to make your queries read only. From like an ease of programming standpoint. Because you don't, like, you're not guaranteed, if you only build it during query, you're not guaranteed that your search paths go this way. So like subsequent searches, if you build it during query, like you could use this pointer that you added, but like your first time, you wouldn't have this pointer. And like, you're never guaranteed to have this
Following
pointer.
it.
Yeah, but like, you're never guaranteed to have this pointer if you only build it upon query, because like your queries might not come this way, or you might not even get any queries. Suppose you only had insert, it's possible.
I don't know if I'm thinking about this wrong, but aren't we just getting back to like, isn't this kind of equivalent to just having a huge B plus tree in a sense?
It's just equivalent to having a huge B plus tree.
I don't think we're just adding like 4 pointers.
But LSMs are dynamic somehow.
Well, B plus trees are also dynamic, but LSMs are faster to insert because they have log n over B. They cost log n over B to insert into.
Oh.
Or so, yeah, they cost log n over B to insert into, where B trees are log base B of n.
B trees, you have to always.
You have to also
to insert.
So, the main benefit here is,
The main benefit is like to speed up your writes
okay.
without losing too much in your read.
So I don't understand how searching each tree is O of 1. Because then we still have to navigate through each B tree to get to a point where we move to the next tree, or am I misunderstanding?
So if you build these pointers between each of the B trees, you only have to search the first one. And then if the pointers are between like the leaf levels of each B tree, then you can just jump between the leaf levels of the B tree and you don't have to traverse the top structure.
That makes sense.
Yeah, good, thank you. Cool. Good that this still works. Yeah, so basically you build this structure not upon query, but upon insert, because you're never guaranteed to have query. Like you may have a workload that's insert only or delete only. And so, yeah. Okay, so in this example, like these pointers are redundant because they go to the same memory block, so we don't need to keep them. And so we can remove the redundant ones, like here, E goes here and W goes here, but it's the same block and we only need one pointer per block. Okay, and you have some blocks that didn't have any pointers into them, so we have to add these ghost values that are the front of each of these blocks in the later trees. So this guarantees that you have one pointer per block.
The ghosts are the pointers, not the elements. The elements are already there.
No, here like H and M were not there before, but you have to kind of like make them take elements to get the pointer into the later section.
Where are you, like, what if that, like that leaf? Or I guess it doesn't matter because it would just move over, it, but like. I know, I guess that's not.
Does this affect deletion? Sorry, if you're saying like if you knock out B, like what would you do? You could build a pointer from E. Or you would have to you would knock out B, and then in the next rebuild, you would have to make A a ghost.
And I'm assuming there's something that would indicate that this is not like an actual value.
Yeah, like you would need another special value, just like Tombstone, you would have another reserved value for this.
So, and what's the problem of not having those? I don't really get it from this slide.
Oh,
I don't know
because
what's the problem, it's like, it would make it more. it's like-
Because you're not guaranteed if you only build from the elements that you have, you're not guaranteed to have a pointer per block.
Okay.
And
But-
so you need a pointer per block to bound your search.
Yeah, okay, I get this. Then we kind of like violate the whole B plus tree thing when we say that we've got to have like this and this amount of number of elements in the leaf, right? So what's the bound there? Do we have any upper bounds of, yeah, sure, we have upper bound because we have a limited number of leaves in the next tree, but so we can put all of them inside the leaf, right? And there is no like limit or boundary there.
Can you say it again?
Is there any upper bound for the leaf to have any number of children?
The leaf is, like, the leaf has a fixed size. It's like bounded by B.
Yeah, yeah,
theta
but
B.
ghost then doesn't count, right? Or do
It
they
will
count?
take space inside the leaf. So you would just like cut the leaves.
So they take space. Or
Yeah,
don't
they take
Okay,
space.
okay.
Pointers
So,
take space,
uh,
ghosts take
Yeah,
space.
okay. Because from this slide, I was assuming that we have size of 4, and then suddenly we have 6 elements in the leaf, and that's why I was confused.
Oh, I see. No, yeah, we would have to cut it again somehow. Okay, yeah. So the reason that you want to add this is because you want one pointer per block, because you want to bound how much you have to search in the later level.
So we cut that way we don't have B, E, H, M, P,
Yeah.
W. Like, we don't have a note, we don't actually have a block with 6 in it. We split it into 2.
I mean, this, like, it could be that B equals 6, and this is just,
Yeah.
these leaves are just not full.
What if it was full? Then do we have to split it?
Then we would have to split.
And H and M are.
H and M are.
Are they big members, or do we actually copy the values for H and M over? Or is that on choice?
I think it's like these choice, you can, yeah, unless you have tombstone for each of them, you could just copy them over. Cause like, they're valid elements in your tree.
So it also makes it so that, I guess that's somewhat of not optimizing, but you might find more. But
Yeah, so like it might, so, you might, well, yeah, you might just copy them over actually, because,
basically like.
they're in the tree anyway.
Like for every leaf in like T of J, I plus 1, like the beginning of that or something pointing to it needs to exist in T of, and the leaves of T of I. Okay. Got it.
So why do we call them ghosts then, if we would have anyway for every leaf, a pointer in the tree behind it?
Maybe because they used to be present here but are no longer.
Okay, but semantically it's the same as
Yeah.
forwarding pointers, we just
Yeah.
like say.
It's
okay.
like adding them back,
Yeah, pretty much. It's like moving them back from, they were flushed here at some point. So they have to come
but
back.
we're intentionally duplicating as well.
So when we do this, now you only need one IO per tree, because once you search into the earlier trees, you can follow the pointer, and you're guaranteed to find either your element or the next forwarding pointer in this block. Does that make sense?
Because you get the entire block at once, and then you can check, like that counts as 1 IO.
Yes, this entire block counts as one IO, and you're guaranteed to either find it in this block, or you may have to follow it to the later block, but you're guaranteed that the next forwarding pointer is in this block, because otherwise you would have gone to the next one.
Okay.
Does that make sense? And so that is how you do build these forwarding pointers, and because you only have to do one IO per tree now your search is log base R of n, where R is the number of trees you have.
What? Can you explain that migration?
Yeah, so
Great question.
like the number of trees you have is log base R of n.
Oh, yeah, the number of
Sorry,
trees you
yeah,
have.
the number of trees you have is log base R of n, and you had to do one IO first. Oh.
But
Sorry, no, I meant the whole
the
thing.
whole thing is.
And R is like the constant by which your trees increase.
So that you won't be using the pivots when you're searching essentially.
Yes, now you don't need the pivots. You just need to keep the lower level. So now it's not really a tree anymore. Now it's just a bunch of arrays, pretty much. Because now you're just using these 4 pointers. Like you're not traversing the top level of your B tree anymore.
Can you repeat that? I didn't hear what don't we use?
You're not traversing like you used to have like higher levels in your B tree,
Okay, yeah.
and now you're just using these forwarding
Okay,
pointers.
so basically, we just done.
Yes, pretty much.
There was that in the source. period. So,
The first one, you can do like a binary search or something.
on the last, yeah.
Yeah, and then like the first one, you could do any kind of search, like linear or binary, and then you
Yeah, that's
follow
equal
the
to,
pointers.
Hmm? That's equal to going to the level, just log in.
But normally with the levels, you get log-based P of n.
Wouldn't it have to be, I don't understand how it's log based are, it's like, wouldn't you have to search like some levels in the tree? Like,
The lower, like you might have to search the first one, but everything after that, you just follow the pointer.
well, everything after you follow it, until you that it would be.
And then you may have to keep going, but the number of pointers you have to follow is the number of trees you have.
So, and then do we have then this whole tree structure for the following trees only that we know how to order the leaves? So we
You
still
see?
store it, right? I mean, we still store trees, even though we don't, right?
You can just store arrays.
Okay, but how is it usually done? I just like three
Oh.
arrays of store or? Because
I
I
see.
didn't think why we would need like this whole tree structure other than the way how we actually
Yeah.
sort the leaves is basically defined by the way how we constructed the tree, right?
Yeah. So yeah, you don't need to store the tree structure anymore.
So once constructed, we basically say, it doesn't matter.
Yes.
Did you say binary search in the last level is better than transformative?
You can buy, no, you just need to binary, the first one, you don't have any forwarding pointers to go into the first one, because it's like just the first one. So every subsequent one after the first one, you follow the pointers.
You know, when asking for the first, you can either go binary to the last level, or you can have, you can traverse the tree.
But
Yeah,
basically-
either way is fine, but like,
Yeah.
yeah, but in terms of like a big O sense, that one is the smallest one, so it doesn't matter what you do.
Yeah, that's all.
Yes. Okay. Good. So if we put all these things together, you have, originally we had this LSM tree and we added these forward pointers and we add these ghost pointers. And this actually comes up with this new data structure that's called this cache oblivious look ahead array. So like we were saying, you don't actually need to store the top levels of the tree anymore. You only need to store this contiguous array in the bottom with these forwarding pointers. And yeah, you can just implement these with regular arrays at every level. And that's how you get back to this optimal thing.
So you still need to do the B tree in order to construct it, and then you can throw away the internal nodes and turn it into, you need to do the B plus to construct it, and then.
Now with this, you only need to keep the arrays. Like you never need to
I
keep
think
the
it's
top
like, you can
levels.
still construct it like this, like, if you only have the arrays per tree, or per like, the object, like, then you can easily, like, once you like flush, you can construct the pointers and do that thing, so you don't need to have a tree structure anymore.
I mean, like, this is kind of like, where's reinventing B tree though, right?
We're just
Like, this
reinventing a
looks a
feature.
lot like,
Oh, yeah.
this looks a lot like a B tree, but sideways.
Yeah.
Yeah, but the bounds are different.
Yeah, and that-
The
that's-
insert bound is log n divided by b. Whereas the B tree insert bound is log base b, and then. That's why we did the reason that we had to go through this whole complicated thing is because we want to keep the right optimization bounds of amortized right cost. So we don't have to traverse all the way down like we would in the B tree.
So do we actually, in this version, like separate the elements as we did with the leaves, or do they just continuously store it in a way?
Now
Like
they can just be in one,
okay.
now they can all just be in one
Okay,
contiguous
so
array.
we
You don't need
care
to split
about
it
the
anymore.
size of the program.
Yeah.
So-
Yes.
But in a B tree, there can be like elements like in the intermediary leaves, right?
Yeah.
So how is this different from that?
This is now just one thing, like it's one array, whereas in a B tree you have like many levels.
Well, no, but you have many levels,
Yeah.
that, and
So
that.
Ti and Ti plus one
Oh,
different.
Because, oh, I see, you're saying like each one of these is
Yeah.
like a level in a B tree?
Yeah.
This is one contiguous array rather than separate, like the leaves, like the nodes in a B tree are blocks.
Would that not just be?
No, usually you implement them as blocks.
Okay.
Yeah.
But if this is better than why best, or maybe it's not actually, right, that's,
Uh,
I think I know, but yeah.
It's not necessarily better, I guess, like
Yeah.
it gets the right optimized bound, but the search performance is worse than a B tree. It's not necessarily like better or worse, it's just like somewhere else on this trade-off curve.
Yeah.
And I think usually, in terms of implementation, this version is not, like a regular LSM is probably more popular than this implementation, but this is like a way that you get cache oblivious data structures, which is you don't need to know the cache, you don't need to know the cache parameters, like you don't need the cache line size to implement an array.
Okay.
Whereas previously in a B tree, you need the cache line
Maybe
size.
after we invest the blocks. size.
Yeah, but like if you don't have the cache line size for some reason,
Well, you wouldn't need to, kind of, just because to know like how often you need ghosts, wouldn't you need to know the cache?
it's a good point. You probably could prove the bounds if your ghosts are every like log n or so. And I will not say how to prove that because it's just probably complicated. Yeah, that's usually how these data structures work. Okay. I want to talk about PMAs. Yes, I do want to talk about PMAs. Okay, I'll be fast. So that was one cache oblivious data structure. This thing that we ended up with is this COLA, which is a cache oblivious look ahead array. Packed memory array is another kind of cache oblivious data structure. And the way it works is that it's this ordered dictionary. So this is a full dictionary. It stores elements in a contiguous array, and it has a constant factor of empty spaces in the array. And the empty spaces allow you to do updates faster than just shifting everything around. So like normally in an array, like if you wanted to insert it in sorted order, you'd have to maybe shift all the stuff down. But now in these empty spaces, you're guaranteed to only have to shift some amount of stuff down, where some amount of stuff is bounded by how full the blocks are. And yeah, so you have a constant factor of empty spaces. So if you have n elements, then you store m is theta n cells, and it's one giant memory allocation, and it's implicitly split into chunks of size log n. And those chunks of size log n are called PMA loops.
Is this a type of fractional cascading, or is this a different?
Oh, sorry, this is a different thing. We're done with LSM trees. Yeah, this is a completely different thing. This is a separate cache oblivious data structure.
What does cache oblivious mean?
Cache oblivious means you don't need to know the cache parameters, like you don't need B or M. I don't really want to talk about how you do stuff in a PMA, so I'm not going to. But I don't know, I do, but like I only have 4 minutes left, so I can upload the slides. I would like to talk about it, but I have 4 minutes, and maybe that's not the most important thing that I want to do with my 4 minutes. All right, so the most important part is that these are the bounds for the PMA. So this is the worst case amortized bound. The insertion cost is log n squared divided by b plus log n. And the way you get this is like, this is how much, you trust me that this is how much it costs to search in a PMA. And you have to do a search to where you're going to put the element. And this is how many amortized element moves you have to do over the lifetime of the data structure.
It's not trivial, you don't have to say, but how is searching log n? Because
The size of the array is theta n, and it's blocked up into chunks.
Right.
And the way that the search works is basically like a binary search on those blocks.
but when you finish a block, you don't know how much empty space is in front of you to make the next jump. How do you do that?
You know, the size of the blocks is fixed up front. Each block is the same size.
Okay.
So you do a binary search on the front of the blocks.
Okay.
And the number of blocks you have is bounded by n, so the search cost is log n.
Okay.
Okay, so this is the search cost. This is way worse than the B tree, which is log base B of n. Like even the search cost alone is worse than the B tree. And again, the search is log n, the insert cost is log base, search cost is log base B in the B tree, and the scan cost is n over B in both. So yeah, so the question is like, why do we even care about this if B trees are at least as good in every axis in a big O sense? And the reason is because the ideal cache model that we have previously, the ideal cache model is a variant of the dis-axis model, which is a more general thing. And again, this counts the cache axes. So in this, every memory block in this dis-axis model has unit cost. So like, this is your big memory and this is your small memory. In this example, you have to bring each of these cache lines into your cache, and each one costs 1 to bring in, so this would cost you 5. But in reality, it costs you differently to access random cache lines versus sequential cache lines. And so there's this thing called this affine model, which is a more refined model, more refined version of the dis-axis model. And in this model, random access has unit cost, but sequential access has cost alpha less than 1. And so here, rather than 5, these 3 are random, so that's 3, but these 2 are sequential, they come right after this one, so that's 3 plus 2 alpha. And we care about this because the PMA is one contiguous allocation, so in this model, it would be faster to scan the PMA. This is just some empirical verification that this affine model does indeed work. So this is the block size that you read memory in. And this y-axis is the time that it took to scan, in this example, of 8 gigs, and down is good. And basically the point of this is that the bigger block size you read, the faster it is to scan the same size of memory. And this is just, this is a small plot to show you what I'm talking about. Normalized performance, up is good, blue is PMA, black is B plus tree. And you can see that the scan performance for the PMA is almost 2 times better than the B plus tree, even though in the ideal cache model or in the DEM, they're equal. But as the theory tells us, the find and the insert are worse compared to the B plus tree. So in addition to this query insert trade-off, there's also this scan like point. There's like this range point trade-off, where scan is a range operation and find and insert are point operations. Okay, I do want to talk about tries, but I'm out of time. But I will upload the slides. Okay, so to summarize, B plus trees are a go-to, pretty much like the go-to in memory indexing structure, also out of memory. B epsilon trees are asymptotically faster to insert without theoretical loss in search performance, but they're harder to implement, and they also have worse write amplification because you have to keep doing buffering. And you see a similar thing for LSM. You have asymptotically faster insert than B trees, but they also suffer from the same issues that buffered data structures have. And I was talking about skip lists last time. They're really good if you don't want to implement self-balancing, because you just can do the randomization. And PMAs and LSM are both cache oblivious data structures, which means that you don't need to know the cache parameters. Yeah, thank you. I am out of time.